Hello and welcome to a little demonstration of a 32-bit calculator project in Minecraft. So let's look at the GUI here. So, whoops. We have an input screen here. There's your first input. Oh, I should first mention this is a 32-bit calculator. So, yeah, you're not going to see many 32-bit calculators in Minecraft. That means that it can calculate up into the billions. You can see we have 10 digits here, and we have 10 digits here, and 10 digits here. So it is capable of displaying numbers in the billions. In fact, it can actually calculate numbers above the billions, it just can't display them. So, currently the functions that I have implemented are, and probably these will be the only functions implemented because I don't think I'll be working on it anymore, are addition, subtraction, and multiplication, so not very exciting. Unfortunately, division does not exist yet. I don't know when I'm going to have time to implement it, if I even want to, but it's there. The button just won't do anything. And of course we have an equals button, so let's demonstrate some single-digit addition first. I will admit that it's not extremely practical with single-digit addition, but let's see. So 2, and you'll notice that the 2 has appeared in the first place on the top. And now let's hit the plus button. So right now you can see I've got these signs right there. So if I hit the plus button, you'll see that that plus sign actually has lit up. And now I'm going to add 2 to 9. And you'll see that a 9 has now appeared in the second row. Okay, so let's hit the equals button. And now we just wait for something to appear on this result screen. Like I said, it's not very practical for one-digit addition, but just wait until we get to 6-digit multiplication, and then maybe you'll change your mind about the practicality. Because this thing has the potential to do multiplication of large numbers faster than you can do it in your head. So yeah, it's actually a Minecraft calculator that's somewhat useful, except not really, but I don't know. I'm just trying to justify its creation. Really, the main reason that I created it was sort of as a learning experience. Ah, and there's the answer right there. 2 plus 9 is indeed 11, so it got it right. That's a good thing. So now we hit the reset button. This red button is the reset button, and you'll see that it will just wipe across the screen, resetting it, and it resets this one as well. And it's also resetting a million other things in the rest of this monstrous thing. Okay, so it's completely reset now. So let's do larger addition now. So I'm going to add let's add 50,000, 54,000. I'm just thinking of these numbers off the top of my head. I didn't write them down beforehand or anything. 54,000. Now we wait for that light to come on. 300. And you'll see every time I put in a new number, it shifts to the left on the input screen. So that's one of the features I've implemented. 360. So it doesn't really matter how many digits you enter in. It'll just keep shifting it to the left. So if you're curious why it's taking so long to enter each digit, well, first of all, it's because I came up with this design myself, and it's probably not the best design or the most efficient. But also, let's put in a 7. what it's doing is it's converting each new number that I create to binary, which is not an incredibly simple process. So every time I add in a number, it converts it to binary. So when I put in the 5, well then it's 5 in binary, which is 101. And then I put in this in the 4, well then it's 54 in binary. Then it's 543 in binary, then 5,436 in binary, and then the full number right now is in binary. Somewhere that binary number is stored. In fact, I'll show you where it's stored. It is stored right here. So what you're seeing here is actually the binary representation of that number, hopefully, unless something has gone terribly wrong. Apparently it has a lot of 1s at the beginning. I did not know that. Now it's a 1, 0, and then it's got 2 1s here, and then it keeps going up here, and there's no more 1s, so that's the end of the number. But you will notice that it has a lot more digits in binary than it has in decimal. In fact, it's going to have somewhere around 4 times as many digits, maybe even 5 times as many digits as a decimal number, which makes sense. So if this has 5 digits, it's probably going to have, 16 to 20 digits. Okay, so there's the first number. Now we're going to hit the plus sign. And there's the plus sign on. Now let's just do a 3-digit number, 860. You see it lines up the place value here, so right now it's putting 86 in binary into the memory. So 860, well, let's just add 860. There is a 0 here if you didn't see it. And now we wait for this light to come on for it to be safe to hit the equals button. So now you'll see we're now displaying 54,367 plus 860. And now we hit the equals button, and then we just wait. But before I hit it, well, I'll hit it. So what you'll notice is that the amount of time it takes to calculate these large numbers in addition is actually very similar to the amount of time it took to calculate 2 plus 9. So the size of the numbers you're calculating actually doesn't change the time all that much. It does change it a little bit, especially when you get the multiplication. It does affect it, but not as much as you might think. Let's see if we can see what's going on back here. We're getting a bit of lag because there's a lot of redstone stuff going on. Not as much with addition as there is with multiplication. And we're propagating. So let's go up to the display and see what's going on. So you'll notice that this number is not the answer, and that's because it's still propagating across the display. This display is not only just a display, but it's also a binary to decimal converter, or more specifically a binary to BCD converter. Anyway, it finished, so the answer should be 55,227. I think that's right. Yeah, that's right. Okay. So the reason that it propagates like that is it enters the numbers through this, actually only through these 2 redstone lines. And this orange one here is the clock. And so this orange one is flashing on and off at a constant rate just to tell this thing when it's entering a new value. And then this one right here is actually the binary value itself, and it enters it in 1 digit at a time. So maybe it's not the most efficient way to transfer the data, but it works. And so that's why it propagates as it goes, as it enters more digits in binary. Okay, so that's some large number addition. So now I'm going to skip to the large number subtraction after this thing resets. And the way it subtracts is actually just by adding. There's no such thing as subtraction when it comes to computers. There's only addition. In fact, there's no such thing as multiplication either. It's just more addition, except it's not quite repeated addition. It's a method that I'm using here. I won't go into much detail. Anyway, so I'm going to do 800,000. Let's do 870. Takes a while to enter these. 872,000. Uh, 300. I'm just coming up with these numbers as I go. And, oh no! Okay, I think I'm gonna have to reset. I screwed up. Because I entered the number, before it was actually done. It might be okay, actually. I shouldn't have done that. 872,311. It might be okay. I'm honestly not sure if it's gonna be okay. I mean, it's entering it fine here, but that doesn't necessarily mean that it's doing okay over here. Okay, so we do have 3 here, so the number should be divisible by 3. The way that I know that is because we've got 1, 1, and 1, 1 is 3 in binary. So if you have 1, 1 at the end of the number, it should be divisible by 3, which means that these digits should add up to a multiple of 3. So 1 plus 1 is 2, plus 3 is 5, plus 2 is 7, plus 7 is 14, plus 8 is 21. So, or no, it's not. Oh my god. Well, that's not good. 14 plus 8 is 22, which is not divisible by 3. Does that mean we have a problem? Okay, you know what? Let's just see what it does. So it could very well be that it didn't go in correctly, but let's see what it does. So let's hit the minus button, and so now you'll notice the minus button turns on, and let's subtract, I guess, a round number. Of course, this calculator, what we might think of a round number like 100,000, this calculator doesn't care about that. It's going to take just as long, possibly even longer, to calculate it with what we would call a round number than it would for any other number, because even though 100,000 may be a round number in base 10, it's probably not in base 2. So, let's see. 100. So now we're just waiting for it to input. So every time I enter a new digit here, it's actually multiplying what I have so far by 10, and that's the whole purpose of this whole honking thing here, is to multiply things by 10. That's literally all it does. Well, it's not all it does. It multiplies things by 10, but the way it does that is it uses adders. So this entire calculator is based off of these little yellow chunks. You'll notice that there are a lot of them. Actually, you'll notice that I'm repeating a lot of stuff here. This was built with the help of MCEdit. So most of this stuff, I just built one of them and then I copied it along the line. So these yellow things here are called full adders, and they use logic gates to add 2 one-digit binary numbers together. And so the output, so the inputs are over here, you can see them. You've got an A input and a B input, and then the outputs are over here. So this is the output right here. It goes up there. And so you can see that each one of these is identical, so I've just copied this down the line. So yeah, MCEdit's been a great help to this project. But anyway, so I have 100 in there. So let's continue entering things. So now it's going to multiply it by 10 again. And you can actually see this happening if we go up here. You can see things happening in there. Maybe. Okay, so 1,000, 10,000. Actually, let's just subtract 10,000 for the sake of time. We'll see if it works. And the number may not have entered correctly. It is entirely possible that the number did not enter correctly. But we'll find out. So we're now ready to hit the equals button. So here we go. So it's going to do some subtraction here. And this calculator is capable of displaying negative numbers. So the next thing I'm going to demonstrate after this is subtracting a larger number from a smaller number. As you can see, it's starting to do things here. But yeah, it is capable of displaying negative numbers, and the negative sign is right there. You'll see that the negative sign is on right now, but that does not mean that the answer is negative. It will go off once the answer is being displayed, if everything works correctly. But it may not have even propagated or inputted correctly, so we'll find out what it does. Now the minus sign hasn't gone off yet, so that could be a bad sign. Yeah, I don't know what it's doing. Yeah, that doesn't look good. That does not look good. Yeah, so it's obviously wrong. It's a negative number, and it's also, well, not the right number. So let's just give it another chance, shall we? Because I accidentally entered a digit before it was ready, so I think it's fair to give our little calculator here another chance to show off its magic. Okay, so it's done resetting about now, I think. Yeah, okay. So let's see if we can enter a number correctly this time. In fact, I'm actually going to demonstrate the subtraction and the negative numbers at the same time. So let's do a 6-digit number, 200. Actually, let's do a 5-digit number. So 23,000. So now I have to wait for this light to turn on, and then it's okay to enter the next digit. As you can see by that last attempt, you really do have to wait for that light to turn on. Could I improve this design by making it possible to enter numbers in faster? Yes, I could. I mean, in theory, I could have the user input the digits independent of the actual conversion to binary. But the way I have it set up right now, it's converting numbers to binary as I go. So the current design I have does not really allow me to speed this up. Like, this is as fast as I've been able to get it. So I wouldn't exactly call this thing optimized, but it works as long as you don't be mean to it. So now we've entered the number, and I'll hit the minus button, and the minus sign turned on. Let me just make sure everything reset, actually, because occasionally it doesn't reset properly. Yep, everything's reset. Okay, just making sure, because I need to make sure. Okay, so now let's subtract a 6-digit number, and so we should get a negative number from this. We should. Let's subtract 4. 4. I'm not going to be very creative with this number. Or maybe this is creative, it's all a matter of opinion, I suppose. 4, 4, 4. And we're waiting. And a fourth 4. And a fifth 4. And so, well, yeah, I still need another 4 actually to get our 6-digit number. And finally, the 6th 4. Okay, so here's our final subtraction problem. We got 23,571 minus 444,444. So let's see if it works. So yeah, we got that and we got that. So we'll hit the equals button. Here goes the equals button. Boop. Okay, so now let's back up and see what happens. This is the exciting part. Maybe not, because you're waiting for it, but yeah, so I have no idea if it's going to work, but we'll see if it works. Alright, good. It knows it's a negative number, so that's a good sign. Let's see if it starts propagating here. Alright, so now we're at the 100,000s, and here we go. So it is a large negative number, so we know that. That's a good thing. And here we are. So 420,873 is the result. Negative, by the way. And if you want to do that out on the calculator, I'm pretty sure it looks like it's about right. Exactly right, actually. So yes, there's a demonstration of the subtraction. And so now, well, let's try out the multiplication. So I'll hit the reset button again. It's just gonna erase everything on the screen. Basically, the reset button it jams these displays with all ones, and so it sort of just propagates down. And there we go. So it's done resetting. So let's do some large number multiplication. Now this is where you could actually consider this thing to be practical, but as I said before, the main reason why I created this was not for it to be, a useful tool, but it's sort of as a learning experience in logic and learning how calculators work. Because the methods that I've used and the algorithms that I've used in this machine are pretty much exactly the same as you would find in a real calculator. So I could have built this same thing with actual circuits, but of course I would need all the materials for that and all the transistors and whatnot, and that's a lot of stuff to get together, so it's much easier just to do it in a game with a user-friendly interface like this. Of course, redstone certainly does not work the same as actual electricity. The physics are just non-existent, the physics of actual electricity. But the logic is here. The gates that are used in actual calculators are present in here. So let's see, I'm doing 3,204, and let's multiply it by a 5-digit number. So if we multiply a 4-digit number by a 5-digit number, we should end up getting something like an 8-digit number, or maybe even a 9-digit number. It should be a 9-digit number, actually, which this calculator is capable of displaying. Whoops, I accidentally entered another one, that's fine. So I'll just wait for it to finish here. And then we'll hit this lovely button right here. It's the glorious multiplication button. And there are multiplication lights on, yay. So now, let's enter in 4. I'm not doing the 444 again, I'm going to do 40. And we're waiting, and we're waiting, and we're waiting, and we're waiting, and we're waiting. 4. Zero. And that's my multiplication there. So I'm multiplying 32,045 by 40,040. And so let's hit the equals button and see how it does. If you want to time this, feel free to see exactly how long it takes. In my experience, it's been somewhere around between almost a minute, like 50 seconds, and a minute and 40 seconds, somewhere in that range. So let's hit the equals button. And if we come back here, we can actually see some of the processes unfolding. So this is actually a shift register. I'm not going to go into any detail in this video, but that's what it is. It's shifting the number this way. You see it just shifted, and then it just shifted again. So let's see what's going on. If we go back here, we can actually see these lights changing. Again, I'm not going to go into a lot of detail in this video. And let's see what's happening on the display. Hasn't started propagating yet. It does take longer, obviously, to do multiplication, but not a whole lot longer. And this would take a while to do by hand. Maybe not that long, actually, because you could just multiply it by 4,000 and multiply it by 40 and add them together. But here it is, it's starting to propagate. So we're in the tens, the hundreds, and you'll notice that every time it propagates, it might be hard to tell, but it's pretty much multiplying the number by 2. And then it might be adding 1 or it might not be adding 1. And whether it adds a 1 or not is based on whether a 1 or a 0 comes into the display. Alright, we're up to the 100,000s, that's a good sign, and we're still going. 500,000, a million, 2 million, 4 million. So you'll see it's pretty much multiplied by 2. 8 million, 16 million, 32 million, 64 million, 129. And there is the purported result, 129,461,800. Now, the real question is whether that's right. So, let's see, 32 times 4 is 128, so pretty close to that. And 5 times 40 is 800, so you can check this with a calculator, but I'm pretty sure that this is right. So there you have it. That's a demonstration of the multiplication, addition, and subtraction capabilities of this machine. Just a demonstration of digital logic in Minecraft, sort of just a learning experience. And if there are any requests to learn in more detail how the different functions, the different parts of this work, I could go into more detail in a lot of aspects of this. I've constructed it. Pretty much all of the design is my own design. So yeah, thank you for watching.